Okay, and so now for the last talk of the morning, it's a pleasure to introduce Svihla, who is going to talk about sparsification of phylogenetic covariance matrices of K-regular trees. Thank you.
Okay, thank you. So just some motivation. Whenever we have a hierarchical data set, we're going to have some sort of associated tree structure that's going to organize the data into clusters so that they're in bijection with the leaves of the tree. These data sets are very common, and when they occur, oftentimes we're interested in the covariance matrix of that data. However, especially for large data sets, these matrices can be large and dense to the point that they're computationally unmanageable. And this is particularly the case in the context of phylogenetic data, where we can have perhaps hundreds of thousands of species and dense matrices with tens of billions of entries. So recent work has shown that when the underlying tree structure is a binary tree, that we can actually change basis to these so-called Haar-like wavelets and sparsify the covariance matrix by a significant amount. So we have plenty of phylogenetic data sets which are non-binary but have the same problem of having these large, dense covariance matrices. So it's a natural question to ask if we can extend this to a slightly broader class of trees, here the K-regular trees. Specifically, we're looking at planted, ordered, unlabeled K-regular trees for K greater than or equal to 2. We artificially label the leaves according to the order that they occur in a depth-first search, and we label the interior nodes and edges according to the leaves that descend from them. And we also have an edge length function associated with the tree, and this is going to give us, in the case of phylogenetics, some notion of evolutionary time passing or evolutionary distance. So in a phylogenetic context, what this covariance looks like is basically the shared edge length between two nodes. So if we think of them as species intuitively, this captures our thinking that if two species diverged evolutionarily only very recently, we expect them to be similar, and so to similarly thrive or struggle in the same environment. Converse, if they diverged in the distant past, we don't necessarily expect them to be associated. So we define the covariance to be the sum of the edge lengths along the path from their least common ancestor to the root. And the phylogenetic covariance matrix is just the pairwise entries of this. We can get the same notion of covariance if we think of trait evolution as following a Brownian motion along each of the edges. So here, for example, if we are looking at leaves I and J, which shared their evolutionary history for time delta T1 plus delta T2 before diverging, then we would get that their covariance is just a function of their time and some factor which you can think of as maybe being a rate of mutation. So again, these covariance matrices are most often dense or almost fully dense. For example, this is a binary phylogenetic tree from the 97% green genes data set. It has about 100,000 leaves or species. And the covariance matrix has about 10 billion entries, about 94% of which are non-zero. So this is a huge challenge to deal with computationally, both just to store in memory and to actually work with. I think that this particular covariance matrix would be something like 100 gigabytes or more. But we know that there's a lot of redundant information here from the hierarchical structure. There should be some way that we can represent this more efficiently. And the key to doing so is to change basis to the Haar-like wavelets. So these are an orthonormal basis for the linear space of real valued functions defined on the leaves, and they're essentially analogous to the well-known Haar wavelets, except that we define them in terms of the tree's topology. So we have the mother wavelet, which is associated with the phantom root of the tree, and that is just constant across the leaves. And then for each of the interior nodes, we have one fewer wavelets associated to it than the number of children. So for us, k-1 for each interior node. And each wavelet for that node, the support is contained in the leaves which descend from it, and it's defined to be positive or negative on certain subtrees below that node. So here's just a larger view of that. The effect of the wavelets being defined in this way is that, for example, the wavelet associated with node alpha, phi alpha 2, has positive value on nodes 1 through 4, negative on 5 through 7. And so the coordinate of this wavelet in this basis captures the difference between the average value on the left nodes 1 through 4 and the average value among the right nodes 5 through 7. So that as we get further from the root, we are capturing finer scale information. And lastly, to notice about this basis is that because the support of the wavelet is contained in the set of leaves which descend from the interior node they're associated with, many of these wavelets have disjoint support. The reason to note that is that when we perform the change of basis on the covariance matrix, we find that its entries are weighted inner products between the wavelets. And so whenever we look at the entry corresponding to two interior nodes which have disjoint leaf sets descending from them, then we get a 0 entry in our transform matrix. These sorts of interactions are what's going to actually drive the sparsification of the matrix. But the issue is that we need these to occur quite often to actually get a useful amount of sparsification. Even if half of the entries of a matrix became 0 after the transform, for a lot of data sets, we may still be dealing with something that's just as challenging to work with as before. So to get around this, we first want to notice that whenever you have two interior nodes and neither of them is an ancestor of the other, then necessarily the leaf sets are going to be disjoint, and so the wavelets associated with each of them are going to have disjoint supports, and we get a 0 entry for all of those respective coordinates in the matrix. So here's just an illustration kind of giving that intuition. On the left, we have one where there would be no 0 entry produced necessarily. On the right, we know for sure there would be one for any wavelets associated with U and V. So if we go about counting the number of times this occurs, or counting the number of pairs of interior nodes where we have these disjoint leaf sets where one doesn't descend from the other, then we get a bound on zeta, which here is the proportion of entries in the transform matrix in the Haar-like basis, which are 0. And the most important term here is this ratio of internal path length of the tree and the square of the number of interior nodes. In particular, if the internal path length is much less than the square of the number of interior nodes, then that means that the matrix will be significantly sparsified under this basis. And something to note about this is that this bound doesn't actually depend on the edge lengths themselves, which is essentially where the covariance information is stored. It really just depends on the topology of the tree. But we have a problem still. So that bound can tell us that certain classes of trees, for example, perfect K-regular trees, will be sparsified, especially as they become large by this transform. But we can find classes of trees, such as the K-regular caterpillar trees, where they're not significantly sparsified at all. And so what we really want to talk about is what is the shape of a typical K-regular tree. And to do that, we want to know the expected value and variance of internal path length if we have a uniformly random K-regular tree. And this is a good question for generating functions. So if we say that QZU is going to be the generating function for K-regular trees, where Z is, of course, going to mark the size, and then U will mark the internal path length. And in order to get the expected value and variance that we want, we're going to be interested in the singular points of the function shown here, which is just the ordinary generating function, and then its partial derivatives with respect to U. The ordinary generating function is pretty straightforward to handle. The symbolic method, we get an equation describing it, and Lagrange inversion gives us the counting sequence exactly. Also to note here that the trees we initially dealt with when defining the wavelets had a phantom root. The ones we're counting here technically don't, but the phantom root exists more so as a convenience for defining the basis. The discrepancy is negligible in terms of the degree of sparsification in the end. So this is a well understood sequence, and we can quickly find that it has a radius of convergence of and a singularity at this point zk, which depends on k. But the partial derivatives are not so straightforward. So to approach those, I need to do a quick aside on hypergeometric functions. So power series is hypergeometric if the ratio of its consecutive terms is this sort of rational function of the index of variable n, and it's defined in terms of these coefficients aj and bj. Hypergeometric functions have an important property that we can use here, and that is that we can actually look at these coefficients that define them and determine whether or not they converge on the boundary of their domain of convergence. So a hypergeometric function has a balance S, which is the difference between the sum of the B's and sum of the A's. And if that balance is positive, then it will converge on the boundary. And it turns out that our generating function Q is just this sort of hypergeometric function. It has positive balance, so we'll converge on the boundary of its domain of convergence. And we also have a closed form for some solutions of this. And because we know some solutions of Q on the positive real line, because we know that it converges on its boundary, then we can actually extend these solutions to the singular point itself. And we can evaluate it at the singular point like we have here. Now that we have that, we need this to then, we can apply a theorem by Dermata, and we get that, first of all, we get an asymptotic estimate for this counting sequence. We use the asymptotic estimate more because it ends up with a cleaner result in the end. We already know the counting sequence exactly. But more importantly, we get that the singular point we found is the unique singular point of smallest modulus, and we get a singular expansion about this singularity in terms of these analytic functions G and H. And we'll see that because we can write Q in this way, that makes it a lot easier to find the counting sequences of the partial derivatives. So again, from the symbolic method, we have this equation for Q. Using implicit differentiation, we find that the partial derivatives are linear combinations of generating functions with this form, where A, B, and the function f are changing. Those are the parameters in it. And we can also see that this generating function also has the same singular point zk, and it's also the unique singular point for it. So using the singular expansion of Q that we had before and a good deal of algebra, we can finally work it down where we get an asymptotic estimate for the counting sequences of this common function that we have, and so in turn the partial derivatives. Now we have everything we need to use these well-known formulas for the expectation and variance of internal path length as functions of size of the tree. And these are the results that we get. In particular, we can use this with an application of Cantelli's inequality. And we get that for Cn and Phi are our covariance matrix and our wavelet basis matrix. Then after we do the change of basis to it, as the size of the tree increases, then the proportion of entries which becomes 0 after the change of basis converges in probability to 1, which in other words is for a very large tree, it's probably going to be sparsified to a significant degree. So how does this work in practice? It ends up working very well in practice, most often a noticeable degree better than what the bound would guarantee. So here is a 3 regular tree with about 200,000 leaves and about 40 billion entries in the corresponding matrix, and it's essentially fully dense. But by changing basis to the Haar-like wavelets, we can represent it with only 0.03% of that number of values. In fact, the matrix itself couldn't even really be stored in computer memory except maybe in exceptional cases. And this image was only produced by creating a downsampled version of the dense matrix from its sparsified form. Like I mentioned, we often see a bit better degree of sparsification than what the bound would guarantee. And that's for a few reasons, due to the fact that our counting of the 0 entries was actually somewhat conservative. For one, we just assumed that whenever 2 wavelets might not have disjoint support, that they don't. But because, for example, the first wavelet associated with an interior node only has support on the leaves descending from the first 2 children, the second and not the third or fourth and so on, then all of the wavelets below that node for the first wavelet all have mutually disjoint support. And so we're not counting many of these entries, especially for large subtrees that can make up a good proportion of the vanishing entries. And similarly, we don't take into account the fact that we're dealing with an orthogonal basis. In general, the weighted inner product is not 0, but if the edge lengths are balanced in such a way, then sometimes we'll find that the weighted inner product essentially just becomes the inner product scaled by a factor, and then of course we get another 0 entry. Those both will contribute to us seeing a better degree of sparsification than the bound guarantees, but still that bound accounts for the vast majority of the sparsification, at least in my experience. And importantly, since these are similar matrices, we can do all sorts of computations that weren't accessible to us before when we just had access to the dense matrix, if we could do any at all. But here, I was able to find the 500 largest eigenvalues from the spectrum of this matrix, which alone would be almost impossible to do just from the dense form. So in summary, the Haar-like wavelets can be used to sparsify a matrix. We can find out how well they do this by getting a bound on the degree of sparsification, and with high probability, a large matrix or a large tree will have a matrix that's highly sparsified. And Importantly, this lets us store and manipulate and do computations with matrices that otherwise would not be accessible to us. Thank you.
Yes, from Madrid.
Hello. I don't know if I'm misunderstood, but you are assuming that to obtain those results that the irregular trees are uniform, right? What if does this match well with let's say what you can observe in practice?
I'm sorry, you asked why we were assuming that the trees are regular?
Yeah, when you are computing the expected IPL and the variance
Yeah,
of k irregular trees, you are assuming they are uniform among all
Yes.
possible. Yeah. Is this assumption, and you get the n square root of n expected value for the IPL? Is this a assumption matching well with what you observed? But I can't think of situations where the IPL will be even less than n square root of n on average.
So in practice, a lot of the trees are binary, which does fall into this class. So extending it to k-regular admittedly does have fewer use cases. Looking at different classes of trees, such as k-airy trees, where maybe they have a variable number of nodes, that would probably open the door to a lot more common data sets. But right now, I don't have the details of what that proof would look like. This was just a natural extension of the binary case.
Thank you.
Are there more questions? Oh, yeah.
So you gave the first two moments. Do you think that you get the Airy distribution as a limit law?
Sorry, could you repeat that?
So you gave the asymptotics for the two first moments.
Yes.
Do you think that you get the Airy distribution as a limit law behind this problem?
I'm not sure. I can't speak to that.